Okay, so we learned lines, spirals, lemniscates. Now what we want to do is together our limicons and, okay, so let's review. Immediately, that ways that we can this high line theta. Y-axis cosine circles, we have a point here at the diameter of 6. So the A value is the diameter 1, 2, 3, 4, 5, which means our center is right here. So let's draw the circle. So what we want to say about cosine circles, okay, know that A is equal to the diameter, okay, and the center when you have sine cosine circles is going to be it's going to be A over 2, right? It's going to be the absolute value of A divided by 2, because like here A was 6. What was the, it was the radius of the circle, and it was, so the A value is always the R value is always A divided by 2. So when you have a sine cosine circle, and then it's going to be the different thetas, right? If I have sine circles, the thetas are going to be pi over 2 and 2. If I have cosine circles, the centers are going to be 0 and pi. Okay, so that's one circle. But if we have an R equals A, okay, then the A value to the radius of the circle, not the diameter. And the center will always be 0, 0 when you have R equals A form. Okay, let's go to the next one, a line. Now this is a typo up here, so a theta, sorry about that, theta equals pi over 3. And so what we saw in our notes was whenever we have a line, it's at that radial, pi over 3, no matter what R is, as R moves along, theta is all pi over 3, and that results in a line, okay? And what do we want to, the graph looked like this, I mean the table looked like this. It was, if as theta, always one constant, pi over 3, pi over 3, pi over 3. No matter what R was, let's say R or 0 or positive 4, for every R value, theta was that. Okay, roses. Now, roses are of the form A and theta, and there's a couple rules, remember, about roses. So we know that if n even, then, if n is even, then the number of petals is equal to 2n, okay? If n is 2n, but n is odd, then number of petals n equals n, okay? So we remember that. We also remember that with roses, a cosine rose always has, so cosine rose always has at least one petal on axis, okay? But conversely, a sine rose never has a petal the x-axis. Okay, it doesn't always have a petal on the y-axis, but it never has a petal on the x-axis. Cosine rose all x-axis. So let's look at this particular one. It's a cosine rose 5. So this tells you the length of the, so let's write that down here. It represents the length of the petal. Okay, so this n is 2. So what did we say? There'll be 2n, 2 times 2, 4 petals. Right here, and then a length of 5, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. Okay, so cosine rose looks like this. Okay, that is 5 cosine. Okay, spiral of Archimedes. We remember the formula, R equals A, some number times theta. And all right, and if we make a table, R theta, okay, we change the theta values as we go around the polar plane. Let's just table 0, 2 pi, 3 pi over 2, 2 pi. Okay, as we go around, we have to calculate, plug in theta and calculate r. And we let our calculator do this. So that you, make sure you're in radian mode and polar graphs. Go to y equals, now my equation now is 1 divided by 4 times theta. Plug in your equation. Second table. Let's plug in the values. Well, let's check the table set. Make sure we set the table to by integrals of pi over 2. We'll put pi over 2 in here as the table scale. Second table. All right, here we go. 0, 0. So theta is 0, r is 0. 0. If theta is pi over 2, then r is 0.4. If theta is pi, r is 0.8. If theta is 4.7 or 3 pi over 2, 1.2. And if theta is 2 pi, 6. Now we're just going to graph these points. So we graph the point 0, 0. So go 0 rotation and out 0. Take pi over 2, out 0.4. Go to pi over 2 and come out 0.4. Go to pi, out 0.8. Go to pi, come out 0.8. Go to 3 pi over 2, 0.2. Go to 2 pi, come out. A very teeny fill in. Let's stage. By the way, you can stop and listen again. Do limits. So we have a loop we're calling a dimple, a limison dimple, and then we have a limison cardioid. And we remember that all of these shapes, these do with the relationship between A and B. Let's just list the relationships down here. If we have a loop, A is going to be less. If we have a dimple, A will be greater than B. And a cardioid is A equals B. So we have A is 2, B is 4. We have a cosine loop. So cosine is going to, it's positive, so it's this part of the graph. So I'm going to have a point here, and my point, this end will be A plus, say we have the highest, the high point will be A plus B, and it'll be 6. So 1, 2, 5, 6. Now we want to graph the intercepts. Okay? So we'll graph intercepts. Oops, sorry, these are the y-intercepts. Y-intercepts. They are A. They are A distance away from the origin. A is 2, so it's here and here. Those are the intercepts. The height of the loop. The height of the loop is going to be B minus A. Right here we have 4 minus 2, the height will be 2. All right, so once you graph A, okay, so let's label that. These values represent, this is right here, A inner goes through and down. And what else do we want to say? Anything? No, I think that's it. Y-intercepts are pi. That's how we would graph these. Well, actually, in this case, no, our intercepts. And I'm not looking at what I'm doing. This graph is 2 pi over 2 pi over 2. I graph the intercepts. Okay, that's what those points were. But they relate to A. All right, let's do a dimple. We see that A is greater than B. We know it. Let's go through what is the high point. The high point plus B. So then the dimple itself is going to be B minus A. And then intercepts, and in this case it's a sign, it's a positive sign. Dimple is going to be on the y-axis. So our A value is 4, so it's 1, 2, 3, 4. Now notice dimples do not, you don't put a point at the origin. 1, 3, 4. So instead of pointing a point at the origin, your dimple, your main 6, 1, 2, 6. But then the dimple, these two numbers, which is 2. So now we've got 4 points, and we graph them like make a circle. You're going to come a little bit below and dimple in, and there you go. It's not perfect, but we. Okay, so the dimple is B minus A, the high point is A plus B, and the intercepts have to do A. Okay, they're A theta. Now, in our case, a is 4, and in this case, the a theta. This theta will be 0, this theta will be pi. So if I graph this point, it would be 0, and this point would be 4 pi. Okay? All right, let's go to cardioids. Our last one. A equals b. This is going to be a positive cosine cardioid. It's cosine, x-axis, most of the graph will be on the positive side. The a value is 4. So we actually do, and then 1, 2, 3, 4. And the highest point, though the high point, will still a plus b. So 4 plus 4, 8. 1, 2, 3, 4, 5, 7, 8. Now the difference with a cardioid, there's no dimple or loop. It just in like a heart into the back out up here, and then it comes around. More of a circle. That's a cardioid. So it's not a rounded edge here, but that's a cardioid. If this sign was negative, then the cardioid would across the y-axis. Sign, it would be up here. Most of it would be up here, and you get the idea. All right. Let's just say high point. The intercepts are going to be a theta, and you can call that negative a, but really what we do when we graph it is theta, and we keep the a positive. So, all right, we have a sine lemniscate. We know that that's going to be the 45-degree angle. So we're going to draw there because it's sine lemniscate. We know it's a lemniscate because it's r squared. We know what is the a value. Well, a is the square root of this number, which equals 5. So we graph 2, 3, 4, 5, 5 this way, and we graph. Our lemniscates are very easy. The square root of a squared, which a, the distance from the origin to the poles. From the origin to the ends. I'll say, you could say poles, you could say ends. Remembering that lemniscates always r squared, always 2 theta. You did all. I will see you